Looks like we can start, folks. Welcome back, everyone. Before we get started, I don't have too much by the way of announcements, but I want to mention a couple things that does happen on this Moodle website as you're watching it go from week to week. The due dates are sometimes in a bit of a flux. For example, if we just take extra time on a section, I'll push the due date over so it's always a 1 week turnaround on the official due date. Another thing that can happen is section 7.1 was on this, or excuse me, 7.2 was on this week, but we're definitely going to finish 7.2 on the next week. And so I just push it over to the next one there. If for some reason we have to take even more time in section 7.2, that'd be abnormal, but it would go off to the next week and so on. So that's kind of how these things are going to work. These files, they just land on whatever week we happen to finish them on. And then the due date is always going to be a 1 week turnaround. The time, I just had to put something on there, but it's not specifically at 7 p.m. You can turn in your homework assignment before class, after class. As long as I get it on Thursday, it's considered on time. And as far as due dates go, again, it's mainly pacing. It's about being caught up in the course. I don't have a late policy on homework. So if you did give its assignment to me on August 30th, I'll accept it. I mean, that's improving your grade. It's important to get your feedback on that to help with exams. So think of your due dates as pacing. If you're getting these done by the due dates, you're considered fully caught up with the course and you're in really great shape. And this is a tough course as far as getting behind on. If you have other 4 credit courses, you have to balance it out. But if this is your only 4 credit course, keep in mind it is a pretty significant amount of your time that this is going to take up. So watch out about getting behind. It can happen here and there, but try to avoid getting far behind multiple assignments and you'll be in great shape. Well, that's my announcements for the day, not too many compared to on Monday. Any questions at all then, folks, before we get started? Okay, our goal today is finish up a few more problems in section 7.1 to support those questions there in the homework that we're going to take a look at. Then, well, we did integration by parts, some crazy brand new technique, but I think the next section is actually not as bad in a certain way. Trigonometric integrals, it's all about U substitution. It's something that you could have done, say, in Calculus 1 setting back in section 5.4. There's a little bit more to it, but it's going to feel very familiar as opposed to what we just got through here. But let's give it a try. Here's our next integral, part D on example 3. We have an algebraic function, a logarithmic function, and our goal to start this off is integration by parts will go through as long as we can pick a decent U and a decent quantity for dV. Really, this is the fundamental step, picking a U. If we mispick, that's okay. We'll just try again. Yeah, go ahead. Good call. The acronym right here is saying anything that looks like a logarithm, that's a pretty good choice to make your first operation or your first U in integration by parts. So let's go natural log t here. And notice it's also a great choice. I'm going to delete everything beyond the black line in just a moment, but suppose you went a different route. If you let u be t cubed plus 2t, then the differential is easy to calculate. du would be 3t squared plus 2 dt, but now we are kind of shoehorned on dv. It would have to be that now, natural log t dt, and here's the trouble with this method. Finding an antiderivative for natural log t is as hard as the original question. It's a little bit harder in some sense. That's a problem that's done in the examples of the book you'll see in the reading. It's just like doing cosine inverse. But if you notice that coming up with v is extra hard, what is the antiderivative of the natural log of t? It's t natural log t minus t. And take a look at the example in section 7.1, just another integration by parts to get there. That's an indication that this is probably not going to work. Way easier to differentiate the natural log than it is to integrate it. So that just feels like a natural choice on this one. And the mnemonic here is also supporting that idea. So let me take this off. Exactly. The logarithm really should be picked first for you because complexity goes way down the moment you differentiate it and put it all back together. So dv ought to be this right here, t cubed plus 2t dt, and that's going to be the u in our problem. So t cubed plus 2t dt. Like we mentioned before, you really need parentheses right here to make it totally algebraically correct. I'm not going to be super, super picky. If this was, say, a real exam question, I'd probably just, with my green pen, put the parentheses in as an indication. But there are situations where that does matter, so it's good to be careful with these things. On the next step, we do the differential. Recall this is kind of a review as well in section 7.1. Anyone recall what the derivative of a natural log comes out as? Exactly. So natural log goes 1 over t in its derivative, and dt to build the full differential. Good call. Now next, this one is not so bad. Antiderivative of t cubed, we just use the power rule in reverse. This would be 1/4 t power 4. And I use a kind of system when I'm doing these to check as I go. It's easy to get mixed up in different directionalities. Visualize in your mental chalkboard if you differentiate that. 4 would come down, wipes out the fraction. Power goes down by 3, 2 at 3, and you really go to get the t cubed. Same idea on this one, antiderivative of 2t. Put in t squared, because the derivative of 2t gives the 2t. We wanted the simplest antiderivative, so that does the job. That look right to folks on the start for this one? Awesome. All we do next is fill in the blanks. The blanks in the formula we're about to write. Let's write this as uv minus the integral. And often I can't take a look here if there's any constants I want to pull out. But this 1/4, I'm going to leave it right exactly where it is. I can't pull that out without factoring from here. Just makes it more complicated than I want. So this time, nothing is coming out. I'm just going to put in the integral of v du. So all I've done now is stated the formula. Now we really are just filling the blanks in that formula. So here it goes. We go u, which is a natural log t, seeing the table on the right-hand side, times v, which is 1/4 t power 4 plus t squared. And we go minus integral v again. This time we do want parentheses around these. And I think a lot of people, when you do this and get comfortable, you might just divide t into this one and to this one and put the answer right here. Completely fine to take those kind of shortcuts. Just makes my notes unreadable, so I'll take one extra step. So I'm going to write this in as, for the v right here, put in 1/4 t power 4 plus t squared. Then for the du, put in 1 over t dt. So now it's all combined. All we have left to do is solve this integral. And we're definitely on the right track because this one becomes a calculus 1 integral by where the red dot is. So now it's just a matter of cleaning everything up. Also, honestly, like the natural log to go to the right. It just looks a little bit better, but that's just a stylistic choice. Me personally, I'd write this as a 4 t power 4. Let's make that a readable 4. Let me try again. Plus t squared, natural log t, then minus the integral of. Here I'll do the computation. You always want to simplify your integrand as much as possible, and multiplying by 1 over t is just dividing. So this is 1/4 t cubed plus t dt. So all we have left to do is that integral there. Kind of the world's best integral after we've seen some of the problems we've gone through. Any questions, folks, to that stage? Okay, last step, and then we'll have it. So a little bit of copying in these kind of problems, especially when they get long. 4 t power 4, t power 2, natural logarithm of t. Now this minus sign is a little bit tricky, I'd say. When we go to get this antiderivative, we're expecting multiple terms. So we need to be ready with a parenthesis in order to get this totally correct. This is a point where we could lose maybe 1 point in a 5-point problem, because knowing the negative sign has to distribute through that, I would consider that really part of the calculus. Knowing you're getting 2 terms here in the antiderivative, and that distributes through multiplication. It's not major if you forgot, it would just be a 1-point reminder essentially. So antiderivative here, anyone have what this should come out as? Awesome, absolutely. Then just eyeball it. That's my method of take a look at it really closely. Imagine you're differentiating it. 4 would come down, 4/16 is a fourth, and the new power would be 3. So definitely looks like we're on the right track. Same with this one. Next, I'll go plus a constant. And at this stage, you need to make a judgment call. Algebraically, is there anything much we can do? Well, sure, I could distribute natural log through, I could distribute the negative sign through, but to what purpose would we be doing all that? In my opinion, this is as simple as it gets, really. I have a natural log factored out, a negative sign factored out. Distributing things inside isn't going to allow me to combine terms. It won't really clean up. It would be just as an equal way to write it out. So I'd say this right here is a pretty natural stopping point. We did it, folks, then. That's their work for getting that antiderivative up here. Any questions or comments on solving this one?
I distributed it first before I started the LNT.
This one right here?
At the very beginning.
Up here more, or yeah, right up here. Oh, into those two terms. Gotcha.
That makes you, that's what I did wrong.
Yeah, if you went that route, you just have to solve 2 different integrals and it would work out the same way. Glad you mentioned that because, I think the work might be a little bit longer going that route. So it's just as easy. But if you go this way, it's a little bit more dicey, right? But this way you're just doing one integration by parts, one integral altogether. But really it's much of a more of a stylistic choice how you want to do it. If you find an approach that works, I'm happy with it. Your answer might look a little bit different, but it'll be algebraically equivalent as well. Other questions about that so far? Awesome. Thanks for mentioning that. I looked at this and it didn't even occur to me that, yeah, you could distribute, break it into 2 integrals and solve both of them simultaneously. So that is a great approach on this one as well. Sometimes that is the thing to do. Some of these problems, you do have to do some kind of algebra before you even get started. We'll see that in section 7.2, examples of that. But we did it, folks. That's our first example, or excuse me, our first example with integration by parts, at least. What I want to do next is now look at these things here. We haven't given a lot of attention to the definite integrals, and they are still important in calculus. These things are representing areas under a curve. An area could be all sorts of important physical quantities. It could represent a distance, energy, lots of other stuff. We'd have to look at applications to be sure. But we'll be seeing loads of applications in chapter 8. So let's give this a try just to get some more practice on the fundamental theorem of calculus. We have interesting setup of functions. X would be the algebraic. 5 to the x would be the exponential. And so it all comes down to this primarily. What would you all say is the best choice for you this time? Good call. The algebraic takes this precedence right here. A. The 5 to the power of x is the exponential. So we'll leave that as the dv part. So u is x. Kind of nice. That means dv is going to be all of this stuff right here. 5 to the power x dx. Let me finalize that color coding. There we go. Now, the differential here is nice. Derivative of x is 1. So that whole line in blue becomes du equals dx. But if you're like me, this might be a little bit foggy. These kinds of exponentials are not as common all the time in calculus, but they do come up. So we have to be ready for them when they do come up. Let's do some review stuff here. If y was equal to e to the x, what would you all say y prime should be in that case? Good call. It's like the world's craziest and best derivative all at once. Same with antiderivatives on that thing. So let's change it up. I mean, that is an exponential function. It's just the nicest one you could deal with in a calculus setting. How about if y was equal to, let's make it 5 to the x. Anyone see what this one ought to come out as? Yeah, go ahead.
It's 1 over the natural log of 5 times 5.
You're really close. That would be the antiderivative on that one.
Oh,
So the derivative would be backwards, but you've got the idea on that one. Yeah, exactly. So the answer here would be exactly as you said it. On our table down here, this is more If you were doing the derivative, you'd go 5 to the x natural log 5. And so now finally, here's the big formula. If you want an antiderivative of an exponential to the base of b to a power of x dx, that's much like the 5x we're dealing. Also this one, but it allows for any base, not just Euler's number there. This always turns into b to the power of x, divide by natural log b, as you were saying, for the natural log 5, plus a constant. And the reason that works is, if you differentiate, you multiply by natural log 5. Now, if you do the opposite procedure, find an antiderivative, you divide by whatever the base is, natural log b. But don't forget you have to add a constant too. Except up here, we take the simplest antiderivative, so it all comes down to this. V equals 5 to the power of x, divide by natural log 5. So we're on our way with our table. That should do it for us. Any questions at all on the setup so far? Okay, next step, write down the formula. But remember, there's something new on this problem. It's a definite integral, so we have to incorporate that into our formula. This will go uv, and this is the new portion. If it's a definite integral, just integrate from 0 to 2, whatever the values are for this right here. So we just slap the evaluation here. Now we're using the fundamental theorem of calculus. We go next minus, give it a little space on this one, integral sign. Oh, hang on. Sorry, I'm writing down the formula. This one didn't need a little space. That's on the next step. The formula is going to go uv minus the integral, but it's a definite one. So from 0 to 2, v du. So essentially, this is the only thing that's new. If you have a lower limit and an upper limit, include those in the next formula, and now you're on the right track. Does that make sense to everyone on how we're getting through this one? Okay, looks like we're well on our way. Let me move this mnemonic somewhere else. Yeah, exactly. So we wouldn't add the plus c to it, essentially. Other questions so far? Okay, so let's slap it all together. We have, this is equal to u, which is an x right here, times v. That one's going to be 5 to the x, divide by the natural logarithm of 5, minus, oh, hang on, don't forget the evaluation bracket. Evaluate all of that from 0 to 2, then minus a little bit of space because we have a constant natural log 5 that we could separate out. So integrate from 0 to 2, 1 over natural log 5 going in front, 5 to the x is inside, and a d to the x here. This one's just about done as far as finding the antiderivative, since we've already done it once. We're not going to add a constant at all in this one because we're dealing with a definite integral this time. So let's start by the evaluation right here. We have 1 over natural log 5. That's the constant that doesn't really get affected, so I usually factor it out to the left to clean it up. 2 goes into the place of x, so it's affecting these two functions. So we'll get a 2 times 5 squared minus, now use the lower limit of integration. If 0 goes inside, 5 to the power of 0 is a 1, but it's also just multiplied by 0. So 0 there, minus 1 over natural log 5. That came from this one here that was in front of the integral. Now we do an antiderivative of 5 to the power of x. Sorry, say again? Exactly. So just a whole new 1 over natural log 5 to the x. And this portion will be evaluated from 0 to 2. So it's now just a matter of writing it all out, doing the computations. So over here, this is going to turn into 2 by 25, so 50 over natural log 5. Over here, I have 1 over natural log 5 squared. We have to be really careful how we write that. If I write it like this, it's not really clear what's happening. I might be taking the natural log of 25, or I might be taking the natural log of 5 squared, and those are different quantities altogether. Let's double check that just to be specific. So watch out for something like natural log 5 squared versus natural log 5 squared coming out of different quantities, somehow the parentheses omission or presence is really important to these things. And we meant this. This is one of those things where I'm probably going to take off a point to just make a quick comment. Yeah, go ahead.
Also by ln or natural log squared 5.
Yeah, you could use the same kind of thing we do in trig, like say sine squared 5 to indicate the power. Some people do that for the logarithms as well. If you decide to do that on this problem, I'd say that's completely fine. That'd be well understood. So we've got the constant squared out. Next, it's 5 to the power 2 minus 5 to the power of 0. This is a glorified 25 minus 1. So this is just a 24 divided by natural log 5 squared. One last step. So 50 natural log 5. You know, it's kind of tedious to do this part of the problem, but in all honesty, it's really good practice. It is algebraic in a certain sense, dealing with these quantities. So the more you do this kind of stuff, you're just reinforcing old things. It's good practice. I'd probably leave my answer in this format. There's no real need to find at least common denominator, do extra computations, unless there's an extra purpose to that, if there is more to the problem. So I'd say right here, this is a good stopping point. Things that you could do on your homework is, it's not a bad idea to actually calculate it and see if the number is reasonable, but you don't have to. I made a note on the homework, we're going for the exact answer. If this is on your paper, you would get full credit for that. But you know, there is value in putting it in the calculator. Let's put it in the calculator and just see what the value comes out as. So 50 natural log 5 minus 24 natural log 5 squared gives 21.80. So that's interesting. But you know, this is kind of a small check as well. It's not something we can do in an exam setting, but this is something you can do on homework. Well, I have mostly odd problems, but if you encounter the rare even problem that do come up, here's a check to see if this is even reasonable. Next thing I want to do is plot the function. The integrand is f of x equals x times 5 to the power of x. The domain has to go from the limits of integration, 0 to 2. At Desmos, this one, I think I kind of remember, 0 less or equal to x less or equal to 2. So you put those little curly braces around and it plots it on the right domain. And, well, it's a weird looking function. But the important thing I'm getting from this is above the x-axis. So the area under the curve has to be positive, which means this definite integral had better give me a positive quantity. I really can't tell by looking at it until I calculate it. Yes, that was positive. So there's consistency in the problem. And at the end of the day, again, we're going for the exact answers, but once we do applications, we'll be doing a lot more approximations. So that's how definite integrals go. Does it make sense to everyone on how we get through these ones? Okay, so it's same integration by parts as normal. You just have to remember to put these on. I almost forgot it a couple times. I'm used to doing it as an indefinite. So let's practice one more like this one. Part B is kind of a nastier problem. And I don't ask a lot of crazy problems like this on a real exam, but occasionally you might have some homework questions that come with a hint. This is what it might look like. I don't think I went too crazy on section 7.1, but this was a good one to just review a definite integral when you'd use a u substitution, since I don't think we've done that just yet. So this will be exciting. A good review from Calculus 1. It says, hint, begin with a u substitution. Well, I have a cosine of a square root x. So probably the best bet on that is u equals square root of x. Now, I should pause right here. U substitution is weirder than we think sometimes. A lot of different things happen algebraically in a u substitution that we just don't have the time to talk about in Calculus 1. Then suddenly, if you see u substitution in a physics class, a chemistry class, or an engineering class, you might think weird things are happening. It's what we're about to do right here. U substitution is an extremely flexible method, and here's the reason why. If you take the differential of this, you get a du equals 1 over 2 root x dx. I use a formula right here pretty often for this derivative. So let me just give a quick explanation. The derivative of square root comes up so often that this is a worthy shortcut. D by dx of root x. Thinking in first principles in calculus 1, you'd probably write out this. X power 1/2. Now the power rule's on the table. You would get a 1/2. X to the power of, you're taking a derivative so the power goes down. Subtract 1, which is a 2/2 from 1/2. You get a negative 1/2. Then you can go 1/2 x to the power of 1/2. That's just an exponent law, changing the position of the base x. Then you can go 1/2 root x. And that's such a long sequence of steps that you end up doing a lot in calculus 1, calculus 2. This is a common shortcut I often use for square roots. Does that make sense to folks on that derivative there? Awesome, good to hear that. It kind of reminds me of the natural log. Natural log t derivative is 1/t. Root x, kind of the same, except you throw in a 2 as well. That's how I remember it. So let's go back to the problem though. You might wonder, how in the world does that help us, this u substitution? Here's where it gets weird. Once you get this, keep in mind at the very top of the notes, oh, didn't mean to scribble. On the very top of the notes, oh, I can't use that method to scroll up. No, I can't. On the very top of the notes, I'll just use the scroll wheel. We had this idea about the differential over here, and we made a big deal about these parentheses, for example. The reason for that is dy is considered a dependent variable in the entirety. Think of that as one symbol. Everything out here are clearly algebraic things, but dx is also a variable. This would be considered an independent variable, one single variable there. You can do anything algebraically with it that you would use on anything else. It could distribute through, and that's why the parentheses are so critical for some of these. So here's how it affects us in this problem. Because this is an ordinary algebraic equation, you can rearrange it. Multiply both sides by 2 root x, and you get 2 root x du equals dx. But then you can make a substitution within your substitution because that root x is a u. This whole thing turns into 2u du equals dx. Again, that's really kind of weird, but that's the direction we're meant to go on this particular problem. Well, we'll put that together, but we have a second issue. If you do a u substitution on a definite integral, you now have two choices you can make. But the most often choice our author uses is change the limits of integration. I often will take that step as well, so my work here matches what you'll often see in the reading. And here's how I'll always convey it. That upper limit of 9 is relative to the variable x, so I'll say x equals 9, implies we have a new variable u. We're going to finalize our integration on u and not undo our substitution at all. So we need a new upper limit. U equals, take your 9, just throw it inside where x was. And that's our new upper limit of integration. So we're going from something up to 3. Looks like it's 0, but we'll discover as we go through the motions. So next step, if the lower limit x is 0, that implies the new upper limit relative to the variable u now is going to be the square root of 0, coming out as 0 still. So we have a lot of stuff we're dealing with right here. This is the u substitution, yellow highlighted because of this extra trickiness that happened. Right here, let me also highlight that one. Below we have a change on the limits of integration. And now we can say that this whole thing is equal to integrate from 0 to 3 from these limits of integration. Next, we're going to replace dx with 2u du altogether. So it's going to be 2 coming out here. Here's the u, and here's the du. All that's left over is just the cosine. So we'll have cosine of It's a root x, but that's also now the variable u. So this is how it all comes together. Kind of a strange format, but how does it look to folks so far? Awesome, glad to hear that. And again, these are the kinds of questions that you don't really see a lot in Calculus 1. If it was a homework question that I assigned that goes like this, I would always give this hint. I'd probably tell you use that substitution and algebraically rearrange. So it's definitely kind of weird, but we're getting through it. Once we get to this stage, what would you say the method is to finalize this integral? Sorry, say again. Not necessarily. Exactly. Exactly. The integration by parts you're meaning? Absolutely. So now that we have a function u multiplying cosine u, integration by parts ought to do the job for us. Which means u seems like a funny choice all of a sudden, right? Because if I already have u in the problem, I ought to not start integration by parts by indicating a u. I'll have a conflict of notation immediately. Here's a workarounds for you though. You could use a u hat. That'll tell between the u's. But I think probably a more clear choice is use a different variable. That just depends on the person doing the problem. Some people might think z is okay here, or some people might prefer u hat. So I'd say pick the method that just looks the clearest to you. So I'm going to have a z equals. V is okay as a variable. We haven't used that one up yet. I'll use a dv here. And if I anticipated this conflict of notation, I might have picked, say, not a u for a u substitution, maybe a z for a z substitution. But it's good to see it this way too, because the letters we used, they're truly just irrelevant. So it's good to practice it when it's a different letter and still be able to put it all together. So here's a z and dv. Here we have an algebraic function u, so that should be a good choice for z. Z is going to be equal to u. Everything else is cosine u du, so that goes in for the dv. So here's cosine u du. So here's our integration by parts table. It looks a little bit funny because our conflict of notation, but it's always good, again, to just see what the pattern is, not rely specifically on the choice of variable. Next, it's to the differential, so go dz equals du on this line. Here it's an antiderivative. If it was hyperbolic cosine, cosh, I wouldn't be so worried because there's no worries with positive and negative signs. With a cosine, I would be worried. Is this a positive sign or a negative sign? Good call. This one's positive sign. The derivative of a sine u comes out as a cosine u right here. But that's one of those things where I always double check. I don't just automatically say it. I second check, guess myself just to be extra sure. Differentiate the answer, make sure you have the right thing above. We're about there, and now we're going to pick up right here and finalize. Watch out for that too, though. It must distribute through everything in this integral. So the next concept is you have to go like this. 2 times the result of uv minus the integral of v du. Sorry, say, oh, thank you, it's zv. I'm just so used to saying u on there. I feel like we ought to have a different color this time just to convey that. Let's go with purple because this is strange enough. The integral of zv minus the integral of v du. Oh, hang on. Yes, it would have been the dz on this side. I'm looking at the du on this side, and boy, that is tricky. udz. I appreciate the support on this one, folks. Okay, now we've about got it. Because that's so tricky, here's another way I think about this. I know whatever I'm doing, whatever I call the variables, the first step is to multiply those two together. So it should be zu if I'm looking at it in tabular form. So that looks right. Let's plug that in. Oh, and don't forget, there's also limits of integration going from 0 to 3. So much going on in this problem. Those 0 to 3 came from over here, highlighted in yellow. Let me just make that clearly a 3. So as you can tell, probably not a good exam question. It's just too much going on. My exam questions are more trying to hit one or two concepts, a more of a short and sweet kind of question. It's a timed exam. When it comes to homework, this is a good experience dealing with a problem that just gets so hairy that we need to go really carefully and really think about it at every step. I'm definitely thinking about it at every step at this stage. So next is 2 times. We'll plug in our information. Z is a U. V is sine U. So just U sine U, which should be evaluated from 0 to 3. Next, it's going to be the integral of, here's how we think about it next. For whatever goes right here, you're always taking this result, multiplying against that result each and every time. So if I messed up the formula here, still if you're thinking about the layout of your table and you write it out the same every single time, you've got good protection on the error. So this will be a sine u du. Don't forget the 0 for 3 like I did there. And then close the parenthesis. So we're really close now at this stage. We're through the nastiest part of it all. Any questions at all, folks, on any one of these phases? Okay, let's finalize it out then. We have one more integral, 2 fundamental theorems of calculus to apply, and we get 2 times the result of, first we plug in a 3, and notice the reason we did all this is we do actually save a decent amount of time on average with these problems if we do not return to the original variable u. And even if we did, we would still be taking the root of 9 anyways, so we just took those steps earlier to streamline the work. So we're now using 3, which goes for a u. So it's 3 sine 3 minus the result of, we go to put in 0, well, sine of 0 is 0, and it's times 0, so I'll just put a 0 here altogether. Next, we have a negative sign here. We want the antiderivative of sine, so what would you all put here? Is this positive or a negative cosine altogether? Yeah, it's a little tricky. There's an extra negative here, so if you go plus cosine u, differentiate that, and you get the negative sign that's present there altogether. So again, always go carefully when you're doing an antiderivative with the trig function. It always feels a little bit trickier than expected. But does that look right to folks with a cosine u positive? Awesome. We'll evaluate that one from 0 to 3. And notice we're going for exact answers in this section. So if you see a sine 3, you can just leave it just like that if you prefer. If you do put it in your calculator, make sure you're in radian mode, since anything that we're doing with trigonometry, the assumption is radians unless we put in a degree unit specifically. So over here, though, we can calculate one of those trig functions. Let's write this all out to get 2, 3 sine 3, plus, now upper limit here on cosine u will give us a cosine 3, minus cosine 0. Anyone recall the value for cosine 0? Good call. Good review on the trigonometry for that. We'll be looking more at trigonometry in higher detail as we get to section 7.2. But for the moment, cosine 0 comes out as a 1. Sine 0 came out as a 0, so we just put an overall 0 there. Yeah, go ahead.
Would that cosine 0 not also be positive?
This one right here?
Yeah.
Well, the reason this one's negative is because of this process right here. Exactly. We were going a to b of a f of x dx, which gives us antiderivative f of b minus antiderivative f of a. And that's where this negative sign happened to come from. But that's always good to mention, because if this negative sign survived down here, we would have won another set of parentheses because it would have distributed through, changing a whole bunch of signs. Those are the little details that you start to get a handle on the more you do. Yeah. Antiderivative of sine should be a negative cosine.
Keep that negative sign out front until you use the 3 and 0.
Oh, let me see. So are you referring to this negative here?
Yeah.
It turns out not this time. And the only reason is there was a sign cancellation right here effectively. But if we didn't do the sign cancellation, here's what it would look like. Keep that negative sign right there. It would have came down here, but then in our antiderivative, we would have had to go like that. So the negative cosine u, like you said, is the antiderivative of sine u. But now that we have extra negative signs, they both just cancel out, coming to a positive. Does that make sense with that weird sign trickery on that one? It is definitely kind of a bear right there, isn't it? It's one of those strange things where you get used to it over time, but there's definitely two views at this. The first way I viewed it was, let me see if I can control Z to there. I thought of it as this negative sign. Well, you could do this. Put in right there. It could distribute back inside the integral. And now you can think of it this way. The antiderivative of negative sign has to be positive cosine because the derivative of cosine u is that negative sign. But an equally valid way to view this is keep that negative sign exactly where it is. It copies down to this line. Then antiderivative of sine u becomes negative cosine u. Evaluate from 0 to 3. And then at the end of the day, those two negatives convey into a positive sign altogether. Definitely, sorry, say again?
Witchcraft.
It is a lot of witchcraft all of a sudden. It's weird that the calculus, I mean, this was a really hard one in all honesty, but the calculus like this is not bad, but it's those negative signs that can really run away from you.
What's the kind of the integral rules for sine and cosine seem arbitrary to me, but then in this case, it's just like another proof for why it is that way.
In a certain sense, yeah. Well, we're nearly done. All we have to do is put in the value right here for a 1, and we get this. Altogether, the area under cosine square root of x ought to be twice 3 sine 3 plus cosine 3 minus 1. The only trig function we could evaluate it was that one right there. But we did it, folks. That's integration by parts in a nutshell. The purpose of this problem right here is just a reminder, sometimes these calculus problems get kind of ugly, convoluted, and nasty. If this was a real homework question, and you made a couple small mistakes on this one, I wouldn't say that's abnormal. Missing a negative sign here or there, you might have lost a total of just 1 point, but you're really getting the thrust of the problem, getting down to here, maneuvering through these weird substitutions and integration by parts. Well, any last questions, folks, before we close out this section?
You put the plus the on.
Not in this one case, only because it was a definite integral.
Oh,
If it was an indefinite, like say these ones above, these are the times where we put in the arbitrary constant, if we're missing the lower and upper limits of integration. Other questions so far? Yeah.
On the homework, the first one, number 3,
Mhm.
not asking you to do it, but the integral of x cosine 4x,
Oh, yeah.
is it cosine 4x or is it cosine 4x?
It would be cosine of, I believe, 4x like this if they included parentheses. Yep, you betcha. Those are really good questions as well, because without those parentheses, it is sometimes ambiguous what they're really trying to say. And our author writes our textbook in a way that a lot of math is really written. A lot of mathematicians leave off these parentheses all the time, and it does include a little bit of vagueness on it. Well, let's now go and take a look at section 7.2. We're just making an initial start on this section. And you can tell we weren't really meant to get too far on it because we put it all the way down here on the next week. We'll come back to this section as well when we're here on Monday. But for the moment, here's what section 7.2 looks like. We're less reviewing Calculus 1 now that we're in this section, but we're doing more of reviewing a little bit of trigonometry now. We do a lot of trigonometry in this class, more so than you would have done in a Calculus 1 class for a typical course in Calculus 1. And Calculus 3 tends to use just about as much trigonometry as well. So if it's been a little bit of time since you've seen trigonometry, on the Moodle website, you can take a look up here to see some identities, get yourself oriented on how these go. And our own textbook has an excellent appendix on everything you need to know about trigonometry as it relates to this class. First, this is a little bit of review from a calculus class. I put these here because, I mean, we need them. Here's the derivatives of all of our trigonometric functions. You would have done in chapter 3 of Calculus 1. A lot of information here, but the ways you can think about it are, I think this is always kind of a cool pattern. If you differentiate a co-function, you will always produce a negative sign. Watch out for the hyperbolics. That's not true. An extra negative sign goes here and it's eliminated here. So now the next question is, what are the antiderivatives? And we've been using these all along, right? Antiderivative of sine is a negative cosine. Antiderivative of cosine is sine. This one could have been done in Calculus 1. It's really just a u substitution. Tangent is sine divided by cosine. If you let u be a cosine, you can solve this one. Similar idea on this one. But to me, these ones are really, really weird. I feel like they deserve an explanation because of their oddity. Antiderivative of cosecant is not an easy antiderivative, and neither is secant. And there's even more warnings here. There are many algebraic forms for the antiderivatives given below. For example, it might look funny to you why one has a secant and one has a sine. That doesn't even seem like it's the same kind of pattern. But here's a different formula for the antiderivative of the tangent. Tan x dx is also negative natural log cosine x in absolute value, plus a constant. So by properties of logarithms itself, that negative sign can come inside here, become an exponent. Cosine x to a power -1, not cosine inverse, but to a negative exponent is a secant. That's why that's there. The people who wrote out these formulas decided that negative sign was just too much of a bother, put in a secant, which makes secant and sine seem out of order until you see that's really the only difference. So I felt like before we got too far on these, we were going to take all these formulas for granted. You never have to derive the antiderivative of a tangent, a cotangent, and neither of these two. But I felt like we should do one just for the sake of seeing how it goes. Does that sound right to folks? Okay, so this is not a normal homework question, but it's at least giving us some ideas of where this stuff even came from. So here's how I would start to do this one. And if I'm being totally honest with you, I think I would never come up with this idea in 100 years. It's kind of wild how this came together. The trick is to multiply it by secant x plus tangent x divided by secant x plus tangent x. I'm multiplying by the number 1. I'm not changing the domain because all of my denominators for every one of these trig functions is cosine. So we can think of that as the number 1, keeping x in domain. Weird step, right? But here's why this step actually kind of makes sense. We distribute secant x into that numerator, and now we have secant squared x plus secant x tangent x. Now down below, let's leave that there since that's the answer we're trying to hit. Below we have secant x plus tangent x dx. So what in the world does that give us is the big question I feel like everyone would have when you see this. It just seems like we took something simple and made it horrendous. Why did we do that? Well, it's because I have no clue what the antiderivative is for secant. We probably have, I don't think I have ever in this class or in the Calculus 1 class put down a function which I differentiated and got a secant out. I would have had to differentiate something like that or something similar to it. But here's the magical step. Compare the denominator to the numerator. Suppose you differentiate the denominator. Derivative of a secant x is secant x tangent x. The derivative of tangent x is secant squared x. That tells us if the derivative of something equals something else, a good u substitution is suddenly on the table. But that's just wild, and this is a good indication of what's going wrong with integration. integration is really, really hard, but differentiation is fast and it always has a direct formulaic approach to it. But if you're integrating something, weird methods can come up all the time. Our author calls these ad hoc methods, for example. But here's how we'll approach it. That's going to be our U. If everything is going according to plan, we'll check this out, then du should help us out with this differential. First, I have to get my u correct. I did make a mistake there. That should be plus tangent x. Okay, now we're in shape, good shape. The differential of this, I might need some extra space. Let me put it down here. Goes first derivative of secant. That's secant x tan x. I'm going to write this out the way the book would probably, just to save some space. Derivative of tangent is now a secant squared. Close the parentheses, throw in a dx. And all of this stuff can now be substituted out, and you can throw in a du. That's wild in a way. So now we have integral of 1 over u du. So somehow, some way, someone discovered if you are clever enough and multiply by that, I did not come up with this, I reviewed it before I came to class today, then this enables the integral to suddenly be u substitution approachable, just out of nowhere. Same idea as applying to this one. You would just use cosecant x plus cotangent x, above and below. But we're nearly there, folks. This is a good review right here from Calculus 1. What was the antiderivative of a 1 over u? Good call. This one is the natural logarithm. It's the one and only time I would never put u into the numerator and try to use a power rule. It doesn't even work. This is the exceptional case. We get natural log, the absolute value of u. But then, we need a constant just so I don't forget on the next step. Good form to put it right there. Next, put in what u is, and we have natural log absolute value, secant x plus tangent x. Close that absolute value bar and throw in a constant. And let's double check. That's the integral that we were trying to get from the formulas. So that's kind of unfortunate in a way, right? The trig table for derivatives is pretty direct and fast. You're using u substitutions, maybe a product rule, maybe a quotient rule. But these four, and these two in particular, are all more complicated methods to get it going. Well, any questions at all, folks, on either one of these? Okay, another important thing to reiterate on these is if you encounter an antiderivative of a cotangent or an antiderivative of a cosecant, every one of these integrals you're allowed to take for granted. You don't have to rederive them in your problem. The problems would just get too long. This is just doing a secant, for example. So this is a good list to come back to on the notes. If I involved on a real exam question the antiderivative of either of these two, or these two as well, I would probably give some of that as our formula sheet as well, just so that we don't have to suddenly do something that's really kind of crazy to complete a problem. But that's kind of the gist of this section as well. We found the antiderivative here by simple u substitution, and that's how we're going to find most of our antiderivatives in this section. Any questions, folks, before we take a look at maybe one or two more? Okay, so here's the next one for the set. Example 2, we have several problems we want to take a look at for this one. Our author calls this strategy for finding the antiderivative of sine to a power times cosine to a power. Really, in the end of the day, it's all about a u substitution, and you just want to try something that works. If it fails, try something else and you're in good shape. But still, it's good to have some guidance. When you're picking a u on these kinds of things, what you're looking for is a power that is odd. If you spot an odd power for cosine, the suggestion is sine x should be your u. Likewise, if the power of sine is odd, try cosine x. If both of the powers are odd, it's up to you. I'd probably pick the one with the highest power so that I'm cleaning it up the most if they're both odd. So that's pretty good guidance. If there are no odds, you have to make use of the half angle identities from trigonometry. So these two here will handle if this was sine squared x, cosine squared x. And well, our author said this right here, so I included this identity. This is just a half angle identity. Let me find the right zoom so it actually shows up correctly. So these are the main ideas, but there's even more. We're reviewing a good amount of trigonometry. You'll also notice these things right here. They all come from the good old sine squared x plus cosine squared x equals 1. That's usually the very, very first identity that you would probably look at in trigonometry. I mean, this is where trigonometry is defined on the unit circle, giving us this equation immediately. But there's really 3 identities here. There's the one for sine squared plus cosine squared. There's the one for sine squared x equals 1 minus cosine squared x. And there's the one for cosine squared x equals 1 minus sine squared x. So that's where those extra identities are coming from. It's kind of unfortunate. One trig identity can really have 3 different equally valuable expressions in the same time, but we get used to seeing that as it comes up. Well, I think we're ready to give it a try. So if we have a sine squared and a cosine, the power of cosine is odd. It suggests use u equals sine x. So if that's our u, next step we would take is just a differential. Du is now cosine x dx. And it looks like everything here should work out pretty well. If that's our u, then this du will eliminate this portion right here. And that's just going to turn into a u squared from that substitution here. Really, the only thing we need to resolve next is the new limits of integration, like we did in the last set of notes. So here is where you might find it valuable to just review these kinds of things. Here's my best attempt at a circle. We have 2 angles of value here. One is going to be 0. So here's 0 radians. Here's the one for pi over 3 radians. Once I have that, I usually put this on my diagram. At pi over 3, x-coordinate is 1/2. Y-coordinate is, anyone remember the y-coordinate going here? Is it root 2 over 2 or root 3 over 2? Exactly, root 3 over 2 for that one. The way I memorize it is root 3 over 2 is close to 0.9, so it's nearest to the top. You don't have to draw those out when you're doing your homework sets, but I'll probably throw some of these on as a diagram, just for the sake of reviewing trig as we get through these problems. So next, we had a variable x going from pi over 3 to 0. If x is pi over 3, then that will imply u equals sine pi over 3. Any volunteers for the answer on that evaluation here? How about someone over in Zoom? What would sine pi over 3 come out as? Well, here's one thing we could add to the diagram to help us out a little bit. We need to know how our trigonometric. Sorry, go ahead.
Is it square root of 3 over 2?
Yeah, good call. So the idea here is anytime you put down a point on the unit circle, the y-coordinate is your sine value, the x-coordinate is your cosine value. So think of sine going this way, the vertical, cosine going this way, the horizontal. And just as you said, this will come out as the root 3 over 2. Does that make sense to folks on that trig evaluation? Yeah, there's different mnemonics for the triangle to use as well. Yeah, I'm not too familiar with that one as well, but usually I kind of think of it in this term. It's pi over 4, then you get the root 2 over 2. root 2/2 here. And the way it kind of looks right is because root 2/2 is a 0.7. It wouldn't exactly be the 0.5 right here. So yeah, there's really cool tricks with the triangle, but I usually just resort back to the unit circle personally. I'd say stick with whatever method makes the most sense. And there's other really strange mnemonics as well. At the end of the day, a good table like, say, this one could help us out as well. If we have an angle theta, cosine theta, sine theta, this might be a table you might want to bring on, say, your notes on where you're taking any exam in this class, in case a trig evaluation comes up. If theta is 0, we're over here. And what would you say the cosine sine value ought to be in this case?
I think sine would be 0, cosine would be 1. I'm correct.
Absolutely, thank you. So that's our first evaluation there. Next angle is pi/6. This would come out as a root 3/2 and a 1/2. And notice that's the same values over here, except that they're swapped. So things are going to start matching up as you go further and further. Next one will be pi/4. This is where they match. Like you were mentioning on that triangle, you'll have a length 1, and the sides are both root 2/2. Next value, and I don't think far enough ahead on this. Let's get in some more space. This is going to be the pi/3. And now we're on the diagram that we produced. At pi/3, the cosine value is 1/2. The sine value is root 3/2. And that's what I mean by switching. It's the same values, but in opposite order now. And the last one you would typically put in for a good table on trig is pi/2. And that will give us up here at pi/2. Cosine value is 0 now. The sine value is at its maximum, the y-coordinate at height 1. So those are the major pertinent values. As you go all the way around the unit circle, it's the same stuff. You just figure out what coordinate you're on and decide if it's a positive or a negative value. So this whole table extrapolates entirely around the unit circle. So at the end of the day, at pi/3, sine pi/3 is root 3/2. And these are good review topics for us because once again, we do a ton of trigonometry in calculus 2. It's kind of surprising in a way. Any questions, folks, so far? Okay, let's keep on going through it. We changed the upper limit of integration to a root 3/2. We'll do the same with the lower limit. If x equals 0, then that would imply u equals sine at 0. The radian measurement of 0 means you're here, and the sine value is the y-coordinate. It'd be right here at height 0 as well. So we're going from 0 to root 3/2. And now we can plug this all in together. New limits of integration go like this. Next, we're just kind of going down the line of our substitution. If u is sine x, then sine squared x is now a u squared. Finally, cosine x dx, that's going to be our du. And notice what we've done. We took an integral that doesn't seem super friendly, and we have transferred it into a nice integral. This is our calculus 1 integral. Just integrate a good old u squared as a definite integral. That's the whole strategy in all of these notes. They start off crazy, but then it just turns into something like this with the right u substitution. So we're in the portion of the notes where we're kind of home free, but we still want to be careful. Antiderivative of u squared is 1/3 u cubed. Evaluate from 0 to root 3/2. I like to put parentheses around the function if it's just one term I'm dealing with, and leave that factor here, 1/3, factored out, just so I'm not writing 1/3 a bunch of times. Evaluation would then look like this: 1/3. Here, it's going to be root 3/2 cubed. I'll write it out this way: root 3 cubed, 2 cubed, minus just a 0 from the lower limit. Now next, root 3 cubed. Let's just do that on the margin. I think this one is easily simplified by going root 3 squared times root 3. So just separate out a base. And you get 3 root 3 altogether on that one. So we have 1/3 times. That simplifies to 3 root 3. Divide by 8. Then one less cancellation, the 3's, and we get root 3 divided by 8. So my claim is the exact area under that curve has got to be positive root 3 over 8. Really, the major trickiness is just finding the right u substitution. This gets a little bit foggy if it's been a while since you've done a trig course doing those evaluations. But practice with your trig tables, the triangle method as well, or the unit circle diagram, whichever makes the most sense, the way you learned it best in your trig class, and you'll be in good shape. Any questions at all, folks, on that one there? Okay, well, this is definitely a good stopping point for us. You'll notice these problems are just long, right? So I'll try to not start a problem when we have less than a minute time to get through it. Usually we'll try to end at around 8:05 to 8:07. 8:07 is just a weird time to target, I think. Any last questions at all, folks, then, before we call it a night? Okay, when we come back next class, we'll run through the rest of these notes. So next week is all about this, trigonometric integrals, and section 7.3, trigonometric substitutions. Have a great weekend, folks. I'll see you all next class. Sorry, question first? Sorry, say again? Yeah, absolutely. And glad to hear that, Rhett. Have a good night, folks. Yep, have a good one.
Yeah. Up against the trig, right?
Yes, so, that 7.2 is due for a while, right?
Yeah, that's gonna be probably, let's take a look. It can't be September 2nd since that's a holiday. Probably around September 4th is gonna be the due date on that one. You too.